Now let's go ahead and talk about Simpson's paradox. So Simpson's paradox is actually a statistical phenomenon where a trend appears in different groups of data, but actually either disappears or even reverses when the groups are combined. Another way to kind of think about Simpson's paradox is that it is an extreme case of confounding. In other words, if we look at a data set, the overall percentages between the treatment and control group can actually be misleading because of a confounder. They can even be the opposite of what is actually true. So once the confounder is controlled for by stratification, then we see that this effect either reverses or disappears. So I think this is going to be best looking at an example. Puzzle 1 looks at a 20-year study of British women, and they compared the death rates of smokers to non-smokers. And they found this absolutely crazy result that 23.9% of the smokers had died compared to 31.4% of the non-smokers. So right away looking at this, I'm a little skeptical. It seems like this study is saying that smoking makes you live longer. But the first question asks us what type of study this is, and I know right away that it is an observational study. There's no random assignment to treatment and control. Instead, the researchers are just observing these British women and looking at the ones that chose to smoke and the ones that did not. So because it's an observational study, we know that correlation doesn't imply causation. We know that we can't say for sure that smoking helps you live longer. So the second question asks, could this be evidence that smoking helps you live longer? I'm going to actually say probably not. Usually with observational studies, I say maybe there could be a confounder. Here I'm going to say probably not. There is most likely a confounder. So there could be a confounder. And the table of data is given below. And we can see that they did indeed divide these subjects into smokers and non-smokers. And we can see that if we look overall, these percentages are 23.9 for the smokers and 31.4 for the non-smokers. But I said with Simpson's paradox that these can actually be misleading. Anytime you're looking at an observational study, those overall results are going to be misleading because we're not taking into account the confounder. And so in this study, the researchers actually thought, well, let's look at the people's age because we know that with observational studies, the subjects are not randomly divided into this treatment and control group, so they're bound to be different. They thought maybe the age of people is different in the smoker group and the non-smoker group. So if we stratify or break the subjects into group based on age, let's make comparisons based on similar age groups. So we have the young people, 18 to 34, and their death rate was 2.8% for the smokers and 2.7% for the non-smokers. So essentially, this was about the same death rate. There was no statistically significant difference between those numbers, and they basically concluded, all right, the young people have a low death rate, regardless of which group they're in. The 35 to 64-year-old group, if we look at those numbers, the smokers had a death rate of 26%, and the non-smokers had a death rate of 18.4%. That seems more legitimate, right? The smokers had the higher death rate here. So this is Simpson's paradox in action because we see the opposite of the overall results. The complete opposite. Here for the medium age people, 35 to 64, it shows that smoking actually shortens your life, whereas the overall results shows the opposite. So then if we look at the old people, we see kind of the same thing as the young people. For 65 and older, the death rate for the smokers is 85.7, and the death rate for the non-smokers is 85.5, essentially the same. We're basically saying the old people have a high death rate regardless of if they smoke or not. So what they found out for this study was that smoking is not helping you live longer. If we look at the smokers, they only have, we're looking at just the number of people in these groups, they only have 49 old people, whereas the non-smokers had 193 old people. So this was drastically different. The smoker group had a lot less old people than the non-smoker group. So that we can see that it was the ages that was actually driving this conclusion. The smokers just happened to have a lot of young people in their group, since these treatment and control groups were different, and the non-smokers just happened to have all the old people in that group. So that's really what made it look like the non-smokers had a higher death rate. It wasn't the smoking, it was the age of the participants. So this kind of shows us that Simpson's paradox can be very scary. We see the opposite of what's really true. And if you have a table of data, treatment group and control group, we want to remember we never want to compare the overall results in an observational study. So I'm going to go ahead and write this down. Our summary is that in observational studies, we never want to compare overall groups. So do not compare the treatment and control groups because they are different and there could be confounders. And then worst case scenario, I'll say, or Simpson's paradox could occur. So our summary again is that the groups weren't balanced at the start of the study. And if you stratify based on age and compare young people in treatment to young people in control, you actually see that there's no difference between the smokers and non-smokers. For the middle-aged people, we know now smoking takes a while to catch up to you. So for those people, the smokers have a higher death rate. And then the old people, smokers and non-smokers, same death rate. So the second puzzle says, can Simpson's paradox occur in randomized controlled experiments with large sample sizes? Why or why not? And I think this is a great question. Let's think about it from what is Simpson's paradox? I said at the beginning, if I scroll up, I said Simpson's paradox is an extreme case of confounding. And confounders are differences between the treatment and control groups. Randomized controlled experiments shouldn't have those, right? We shouldn't have any differences because we're randomly dividing the subjects. Any differences with large enough sample sizes should average out. So because there's no confounders, there are no confounders in randomized controlled experiments, the nice thing again is that Simpson's paradox can't really occur. So we've talked a lot about how these randomized controlled double-blind experiments are ideal, and this is just another reason that that's the case. So to answer this question, I am going to say no because they are random and do not have confounders. So if they don't have confounders, there's no need to worry about Simpson's paradox. There's no need to worry about differences between the two groups. And if we can, that's what we want to do when we're designing our experiment.